So our next speaker will be Anna, who will be telling us about causality and semantic separation.
Hello. Okay, thank you. I'm Anna. I recently finished my master's in CS at MIT, and today I'll be talking about a semantic characterization of deseparation. So this work lies at the intersection of programming languages and causal inference. Our goal is to give the standard graph analysis in causal inference, which is called deseparation, a formal semantic characterization, analogous to how program analyses are justified by semantics in PL. So this is important because a formal semantic characterization can explain precisely what property deseparation is actually capturing and why its graph rules are correct. Let me first give a brief intro to causal inference. So it is the framework used to reason about cause and effect relationships and to design experiments. So it studies whether variables are causally related and whether an experiment could identify those relationships, perhaps after conditioning on other variables. The key object here is a causal model, which is a DAG describing how variables could potentially influence one another. So in the example on the right, we have the node prior knowledge being able to affect study time as well as test score. And we might wonder whether the amount of extracurriculars that one participates in can have a direct effect on test score after maybe we condition on study time and prior knowledge. Now, deseparation is a purely graph structural criterion, and it determines exactly when variables can influence each other after conditioning on other variables. And so this question could be rephrased to, are extracurriculars and test score deseparated, conditioned on study time and prior knowledge? And this is equivalent to the widely known notion of conditional independence. So from a PL perspective, deseparation looks a lot like a static analysis. It determines what influences what based on graph structure alone. However, it's lacking a formal semantic characterization. And so we introduce semantic separation. We prove that it is equivalent to deseparation, and we fully mechanize the whole development in ROC. This lets us interpret deseparation using concrete behavior rather than graph structure alone. It also provides an experimental interpretation of the predictions given by deseparation, which we'll see towards the end of the talk. So now I will describe how to determine deseparation. The basic idea is that influence propagates along paths in a graph, and conditioning can either block or open those paths. And then two nodes are deseparated, conditioned on a set of nodes, if all paths between the two nodes are blocked by nodes in the conditioning set. And again, this is commonly used in causal inference, in experiment design to determine what variables need to be controlled for. So our example here contains the three ways in which a path of three nodes could be oriented. And as I go through these three rules, try to notice how they are asymmetric and as a result, maybe unintuitive, which motivates our semantic definition. So in the first case, we have influence flowing through S, and so conditioning on S blocks that influence and blocks the path. In the second rule, we have a common cause of S and T, and so conditioning on that common cause also blocks the path. In the third case, which is the unusual one, S here is called a collider, and S actually blocks the path by default, but then conditioning on S creates a dependency between its parents. This third rule is also more complicated than what I will put on the slide. It's also the hardest to explain semantically. So much of the subtlety of our semantic definition comes from trying to explain this behavior. Now going back to our example, if we condition on study and prior knowledge, we can use these rules to determine whether extracurriculars and test score are deseparated. So by the first rule, the path E to S to T is blocked. And by the second rule, the path E to S to P to T is blocked. And so E and T are deseparated, conditioned on S and P. Now, what's interesting is these three rules completely determine deseparation. And you might be thinking it's not super obvious why they correspond to causal influence in the underlying graph structure. And so we found ourselves asking, why are these graph rules correct? And what semantic property are they actually capturing? So we set out to define a semantic version of deseparation. At first glance, it might seem natural to define the semantics using probability distributions, since deseparation is often presented via its connection to conditional independence. However, deseparation itself is purely graph theoretic. So whether two nodes are deseparated depends only on graph structure, and we therefore thought that our semantic definition should also depend only on structure and not on any particular distribution. So far, we've been treating causal models as graphs, but now we need a semantic representation for those graphs and a way for nodes to obtain their values. Fortunately, we can use the standard model in causal inference, which is called a structural causal model. Think of each node as having an associated function which computes the value of that node from the values of its parents. And so, for example, the function for study, or S, could look something like this. But this model, as I presented it, is a little too naive because in practice, we can never realistically model everything that affects a variable. So for example, study could maybe also be affected by course load or stress level or other factors that we did not record. And so the model introduces an additional input to every node's function. This is called an unobserved term, and they're shown here in gray with an arrow to the specific node that it corresponds to. And so the function for study could additionally rely on its unobserved term, which is U of S. Now notice that once we fix an assignment of unobserved terms, the entire model becomes deterministic. So every node's value is fully determined by just repeatedly applying the functions throughout the graph. So then we can think of a world as just a particular assignment of those unobserved terms. And by changing those assignments, we can compare and reason about different worlds. So we're now going to define the semantics of two basic operations that will be useful in our semantic definition. First, what does it mean to condition on a set of nodes? So it simply means we'll restrict our attention to worlds where the values of those nodes match their target values. For example, in this graph, if we think of prior knowledge as being measured as the amount of material that one already knows on a scale from 0 to 1. Then if we want to condition on prior knowledge equaling, say, 0.2, then any world that properly conditions on P is just one in which f of P equals 0.2. And in the case of this graph, that depends only on U of P. Now we need the notion of changing a variable. So we say to perturb a node means to modify the unobserved terms in a controlled way to change the value of that node, and then observe how those changes propagate through the graph. So for example, if we want to change the value of extracurriculars, maybe from 3 to 4, we would start with modifying its unobserved term, changing the value that we want, and then this can propagate and affect downstream variables, study and then test score. So recall that earlier we were interested in, if we condition on study and prior knowledge, whether extracurriculars and test score are deseparated. Now that we've defined the semantics of conditioning and perturbation, we have a way to ask a more semantically precise question that kind of sounds like the deseparation of two nodes, which is, if we perturb the first node, in this case extracurriculars, while maintaining conditioning on the condition set, can we force a change in the second node, in this case test score? So we'll now attempt to define the semantic separation of two nodes, x and y. The simplest idea is change the unobserved terms in a way that affects x, and see whether y changes. But this is too permissive because it allows for changes that are unrelated to the causal structure. For example, say x and y are completely disconnected nodes. We would expect for x to never be able to affect y. But if we happen to change the unobserved terms of both x and y, then y can be affected by a change having nothing to do with x. So we need to restrict our attention to the unobserved terms of nodes that can actually affect x, which leads us to think about ancestors, since recall that a node's value is computed using the values of its parents. So we will restrict changes to what we call unblocked ancestors of x, which are ancestors that have a path to x that does not go through a conditioned node. This captures causal structure better, but it fails in collider settings, where conditioning can create dependencies that are not captured by ancestry. So for example, if this middle node here, w, is the XOR of its two parents, and we want to condition on w equaling 1, then we would expect for x and y to not be semantically separated, because say if we wanted to change the value of x to 0, the value of y would have to change to 1. But this is not captured by the unblocked ancestors method because we can only change ancestors of x. And so if we change the value of x to 0 using its ancestors, that will propagate, and the value of w is now no longer properly conditioned, so the whole system doesn't make sense. We might then attempt to enforce an additional repair step where we allow the changes to propagate, which could affect the conditioned variables. And then we allow for an additional step of repair where we make the required changes to recondition those variables. Here's an example of when we might actually need repair. So suppose we're interested in whether a drug affects reaction time. And we know that this drug affects blood pressure, which affects reaction time. And so in order to isolate the effect that the drug has on reaction time directly, we condition on blood pressure. Then once we administer the drug, we could affect a subject's reaction time. So we might use some other common well-known drug for blood pressure to counteract that effect. So that's us propagating the change that the drug made and repairing the value of the conditioned variable. But this still doesn't quite work in the case that there are multiple conditioned nodes where one repair step might not be sufficient. For example, suppose we have another node, sleep. We know that the blood pressure drug causes extreme sleepiness, and sleep also affects reaction time. Well, then we also need to repair sleep. And you could, of course, imagine we had several more nodes that are conditioned on and would need to be repaired. So this kind of suggests that semantic separation cannot be defined as a single-step notion. It should instead be a multi-phase process. So the fix for this is to allow for a sequence of worlds which represent step-by-step modifications. So our final definition has three main ingredients. First, a catalyst step makes changes to the unobserved terms that are allowed to affect x. Next, we let those changes propagate through the deterministic functions of the graph. And third, if any conditioned nodes have been disturbed, we allow changes to repair them using their own unobserved terms. And then we go back and forth between the propagation and repair steps, since each repair could itself need to propagate and could require more repairs. This results in a sequence of unobserved term assignments, where each pair of consecutive assignments we constrain in a way that guarantees that we make changes minimally. At the end, we compare the original and the final worlds. And if every valid process that changes x leaves y unchanged, we say that x and y are semantically separated. Here's an example from the previous slide where we are conditioning on blood pressure and sleep. So we can show that drug and reaction time are not semantically separated by showing some process that perturbs the drug node and, as a result, the reaction time node. So to perturb the drug node, we would have to use its unobserved term that can propagate to affect blood pressure and reaction time. But since blood pressure is a conditioned node, we can repair it using the blood pressure drug. That can propagate to affect sleep, which is also a conditioned node, so we can repair that, maybe with caffeine, and that can propagate to affect alertness and then reaction time. So since we've now changed the value of reaction time, drug and reaction time cannot be semantically separated. And what we fully formalized and proved in ROC is that the notions of semantic separation and deseparation are exactly equivalent. Very briefly, the proof idea for this is to take the contrapositive in both directions. So in the forward direction, we assume that the two nodes are not deseparated, so there exists some unblocked path from x to y. We then construct functions for each node and a sequence of assignments that propagates a change from x to y along that unblocked path. In the other direction, we assume that the two nodes are not semantically separated, so there exists some functions and unobserved terms that propagate a change from x to y, and then we show that there must exist an unblocked path along which that change is actually propagating. So hopefully this slide gives you a flavor of the definition and the proof, but it's of course missing a lot of detail, so if you're interested, please check out the paper and the code base. Now that we have the theorem, here's one way in which it could be applied in an experiment design context. So in a scientific experiment, a causal model is used as the hypothesis of relationships among variables. And so by our theorem, if a causal model predicts that two variables are deseparated, then no valid perturbation of one could affect the other. And if such an effect is observed experimentally, then the model and the hypothesis have been falsified. So here's an example. Suppose we hypothesize that drug has no effect on reaction time after we condition on blood pressure. Now we've turned a graphical property into a testable prediction, which we might test out by repeatedly recruiting new subjects, administering the drug, and then repairing any effect that this has on their blood pressure using the blood pressure drug. Throughout this process, we should observe no change in the subject's reaction time, but if we do, then the causal model and our hypothesis encoded by it have been falsified. So yeah, that's one way in which the theorem can be applied in experiment design, but more broadly, this work introduces a semantic characterization of deseparation, proves their equivalence, and fully formalizes the whole thing in ROC. Yeah, the URLs to the code base and the paper are available here, and I'm happy to take any questions. Thank you so much.
Questions?
Very nice talk. I am Zhang from Peking University. So from my understanding, deseparation can be applied to long causal models, like just a regular Bayesian network. So can you frame up the extent to this case?
Yeah, I think deseparation can be applied in lots of contexts, not just experiment design. This work is kind of the foundation in maybe a longer term project to formally verify experiment design. And so I was more interested in using it in experiment design contexts. But yeah, I think it could be applied in other uses of deseparation as well.
Okay, thank you.
All right, in the interest of time, I think we'll take any further questions offline. Let's thank Anna.